the week number 5. Here we are in the week number 5, stiffness matter for beams part 2. Last week, I think you remember that last week we developed the stiffness matter of the beam. That's we develop. I think for each beam elements there are 4x4 matrix, and we have used Excel, and we also use the hand calculations to use the stiffness matrix. So, and last week also I show you how to assemble the stiffness matrix. Once you get 2 members beams, 3 members beams, you will get K1, K2, K3, and then you assemble those K1, K2, K3 into the big matrix. So that's just the revisions. So first that 15 minutes, we will just talk through the revision. In your assignments, you have 1 questions coming out of this week's. Please complete those questions as early as possible. And there is a second questions coming out of this coming out of from week 4 and week 5. Next week, I think I will not going to go through Abacus software, but next week I have fully dedicated to do the assignment help. I would say assignment help. If there is no any questions, I will perform the revision on that ones, and I will cover some of the typical questions about the assignments. What I suggest, I dedicated this whole 2 hours for students to go through the assignments with me. If you have any questions, if it's stuck, because I think in this week's we have, I think in this week Thursday, we have a due date probably. So therefore, next week I think there is a due date Thursday. So probably next Monday, I have dedicated fully 2 hours for students to finalize their assignments. I will be online with you. You can ask me the questions. If it is top, which equations need to be used, why this, if there is any errors or anything that is stopping you to complete your assignments. That's what I am fully dedicated for that, because I think I talked with the assignments. They say that they are already discussing this Abacus softwares in the workshop. So therefore, I'm fully putting this week for assignment help, so we can smoothly finish the assignments, because I think due to online and face-to-face and all sort of different challenges, there is not much opportunity that's so it's just basically helping you to complete the assignments. So this week's what we are planning to do, we just want to finish this topic on the stiffness matter of the beams. You remember last week we done the modelings. In the modelings, you remember there is a beam elements, there is a location vectors, and in the location vectors, you can identify near node, you can identify far nodes. You have displacements and you have rotations. At each node, you have displacements and you have rotations. So that's the indicators that we use last times. Now for modelings, if you remember that the number in the square bracket represent the member number. Number in the circle with the numbers represent the node numbering. This is a location vectors. And from these figures, you need to identify which one is the fixed degree of freedom and free degree of freedom. So each node has a 2 degree of freedom. One is vertical displacements and one is the rotation. What does it mean? Because that particular point has ability to go either up or down, or it has an ability to rotate either clockwise or anti-clockwise. So that's what it says. Particularly this point only. Okay, if there is any point here that we're not talking about that particular point that we talk about. So based on these ones, if you have fixed and free, so all your free degree of freedoms are low numbers. You can see free degree of freedoms are the low numbers that I put it here. So I hope you understand that one. So if you understand these ones, please work it out with me, and I might need some help. Let's say this is a roller supports. Let's say this is a roller here. Let's say there is a roller here. Let's say this is fixed supports. Let's say this is fixed supports. Now let's put the member numbering. Let's say member 1, member 2, member 3. You no need to worry about these modelings in the exams or in the assignment questions. We have provided you these modelings in advance. So you no need to worry about doing the modeling by yourself or you need to remember anything. You don't need to remember anything here in this subject, as I said. But you need to have an understanding of how the modeling is done. What is these numbers in that square and so on. If I put the location vector here, then this one become near node 1, 2, 3, and 4. So there are 1, 2, 3, and 4. That is a near node and far node that we put it here. Now, help me out. How many total degree of freedom here in these ones? How many total degree of freedoms? Each node has 2 degree of freedom. So how many totals? You can say, what is the total degree of freedoms? For your case here total degree of freedom is 8. 1, 2, 3, 4, 5, 6, 7, and 8. So total 8 degree of freedom. What would you suggest that total degree of this node 2, 3, 4? Yep. So total 8 degree of freedoms are there. Now out of 8, how many free degree of freedom? And how many fixed degree of freedom? Questions. How many free degree of freedom? How many fixed degree of freedom? I can take you back here. This is your fixed degree of freedoms because these points cannot rotate, cannot go. So 5 and 6 are fixed degree of freedom. This 7 cannot go up and down. So number 2 can rotate. So free degree of freedom is number 2 and 7 is fixed. In here you have both are free, 3 and 4. So 3 and 4 are free. And here 8 is fixed, and 1 is here. So you can see total out of 8, I make it 4 fixed and 4 free. Free meaning this point has restricted. This point is not able to go up. This point cannot be rotated. That's the fixed supports. Roller supports meaning it can rotate, but it cannot go up and down. Roller supports meaning it can rotate, but it cannot go up and down. So help me out here. What is your suggestion? How many fixed degree of freedom? Because total 8. Out of 8, how many free degree of freedom and how many fixed degree of freedom? No, it cannot go up and cannot rotate. So it's fixed. So this is fixed. This point cannot go up. That is fixed, but this can free. So 1, 2, 3, 4, and 6 are fixed degree of freedom and 2 are free degree of freedom. I hope you understand that. And if I clean up all these ones to make you better understand that each node has vertical degree of freedom and rotations. 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 Now when we need to put the numbering, we put free degree of freedoms, which are unknown degree of freedoms as a starting point. So free, I think this is number 1 and number 2. So that are free. So you can see these are 1 and 2 are free degree of freedom. And after that, you can put 3, 4, 5, 6, 7, and 8. Right? There is no any rules at which numbers goes first. But when you put the numbering, the free degree of freedom, which is also known as unknown degree of freedom, unknown displacement, or unknown degree of freedom, that's you need to put it 1 and 2. And remaining fixed degree of freedoms, you can put randomly. Okay. Now let's say here again, this one is fixed, this one is roller, this one is roller, this one is roller. Give me a minute, please. Sorry about that. Someone knocking the door, so I just help them. Okay, so now here we have a fixed supports here, and you have roller here, roller here, roller here. Probably 1, 2, 3 members, location vectors, and 1, 2, 3, and 4 are the node numbering. Now in this case, we will have now how many degree of freedoms here? Total 8 again. Out of 8, you can see this one is fixed. So fixed degree of freedom is 2. These will fix 3, 4, and 5. 5 is fixed degree of freedom, and 3 are free degree of freedoms. And which are the free ones? So these are your free ones. Let me remove everything. So this one here, this one here, this one here, this one here. So free degree of freedoms, that's what we want to start. So 1, 2, and 3 are free, and then 4, 5, 6, 7, and 8. Okay, that's how the numbering goes. So let's say you have pin support here, roller supports here, roller supports here. Then again, you can do modeling 1, 2, 3, location vector. There is no rules 1, 2, 3, 4, 1, 2, 3. You can interchangeably work. And here 1, 2, 2. So how many nodes you have? 1, 2, 3, and 4 nodes. Each node has a 2 degree of freedom. So total 8 degree of freedom. And out of 8, this one free to rotate. So total 8. And out of that one, so this let me erase everything so you can see what I'm talking about. From here, you can see this going up, this going up, this going up, and then you have this rotation. And this is, let's say, pin, roller, and roller. So this one would be free. Let's say 1 and 2 is free. This cannot go up, but let's say 3 is free, 4 is free, 5 is free. So there are free from 1 to 5 and fix 6, 7, and 8 are fixed. 6 to 8 are fixed. I hope you understand that. How about now? I can do it again. All right, so sorry about that. Let's do it again. So we have these pin supports, we have roller supports, we have roller supports. And in here, we have 6, we have 4, we have 5, we have 3, we have 2, we have 1. And in here, we have given 5 kilonewtons. That's the informations we have. So if you want to develop the Q matrix, then you can write Q and with 2 curly brackets. How many degree of freedom totals here? Total 6 degree of freedom. So you can write 1, 2, 3, 4, 5, and 6. You can write 1 to 6 in here. Now you can see at 1, there is no any force. So you can put 0 there because there is no any moments acting at 1. Okay, so that is 0. At 2, you have 5 kilonewton. Look at this 2. And you have 5 kilonewtons. Now 2 arrow is up, meaning positive, but 5 kilonewton going down. So we put -5 for 2. At 3, there is nothing. So 0. At 4, there is no force. So there is 0. At 5, there is no any force here. So that's 0. There is no any force here. So that is 0. So that is the whole story. 0, -5. So you unmute yourself if you not understand the Q matrix, the Q force vectors that I develop here. Very simple. How many total degree you put 2 curly brackets? How many degree of freedoms you put it? 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, or 1 to the total degree of freedoms that you can put. After putting the total degree of freedoms, you can use various strategy. You can start with 1 and check whether the one has the first degree of freedoms. Is there any force or not? If there is no any force acting on that, and so what this 0 represent, that this point does not have any external force, does not have any external moments. 1, there is nothing, so that is 0. 5 kilonewtons going down, which is opposite to the 2, which is going up. Therefore, it is minus 5 kilonewtons there. And then 0, 0, 0, 0, 1, 2, 3, 4, 5, 6. That's written there. So Q matrix is there. 0, minus 5 and 0, 0, 0, 0. So unmute yourself if you don't understand to develop the nodal force vector Q. That is called nodal force vectors. Why it is called nodals? Because you are just always representing as at a node. So you don't need to worry about these other forces. It's always at the nodal. No problems, you can understand that. Now, there is a member force vectors, which is the Q0. That is the nodal force vectors. And another one is called member force vectors, which is Q0. Now in here, okay, don't worry, we will come back on these figures, how to use it. What is the Q0 represents? Now these matters, that the stiffness matters that you can see, it does not like the forces coming onto the members. Look at that. When you have force acting on the members, like acting actually on the members, it does not like. It's like it when the force are coming at the nodes. These are your nodes. Right? Node A, node B, node C. If you have force at the node A, node B, and node C, stiffness methods can be used. It likes it. It's help it. But when you have a force other than this node, it does not like it. It does not like it, meaning we need to transfer these force to the nodes. Does it make sense? That this force 32 kilonewton per meter, which is not acting here, but which is acting in the members. So what these methods wants us to do, that these 30 kilonewtons, you need to transfer these loads into the node. You need to calculate these 32 kilonewtons, which is the member force, which is the force acting on that one, to the end, right? So that's what our main goal. At that time, we will use these figures. You can look at that. So if you have a member with the UDL load, if you want to calculate the force going vertically, which is WL divided by 2, WL divided by 2. And if you have a moments, you can put it in that way, WL square over 8. Similarly, if you have a triangles distributed load, triangular distributed load, then you will have WL square over 30, WL square over 20, and 3WL over 20 and 7WL over 20. That's you can calculate. So this force that's acting on the members, you can just transfer it to the, you can calculate them at the nodal force. Now here, if you have a point load, similarly you have PL over 8, PL over 8, and P by 2 and P by 2. If the force acting in the middles, if the force is not acting in the middle at some distance A and B, then you can also calculate these force and the moments. Now, so let's do the calculation here. So you have 32 kilonewtons coming on here. So if I have 32 kilonewtons, so help me out here. 32, that is your W length. Length is 6 meters. So here you can say 32 times 6 over 2. So 32 times 3, which will be 96 kilonewtons force at this point. Here, same thing, 96 kilonewtons. We can use this one, 32 times 6 square over 12. If you calculate this once again, you get 96 kilonewton meters. That is the moment. Therefore, the unit is kilonewton meters. Moment is force times distance, which is the kilonewton meters. 96 kilonewton meters. So that's all good. All good. So what we can do it, what we can do it, we can put those forces, force going here 96 kilonewtons, force is going here 96 kilonewton meters. This force here 96 kilonewtons, and this force is which directions? Direction is important. Don't change those directions. That is 96 kilonewton per meters. So I hope you understand that the stiffness method does not like this 32 kilonewton meters. So what we done, we recalculate that one, that how much nodal force that goes on to these nodals one. So therefore you have 96 kilonewtons and 96 kilonewton meters, that nodal force that one. Now, similarly, you will have 48 kilonewtons. So for 48 kilonewtons, you have 24 kilonewtons, 24. We can reuse these figures, like you have 24 kilonewtons here, and we have 2 meters. So this is 1 meters, and this whole length is 2 meters. So P by 2, which is 24 divided by 2, which is 12 kilonewtons, which is 24 divided by 2, which is 12 kilonewtons. PL on 8, 24 times 2 over 8, which is cancels 3, so 6 kilonewtons meters, and similarly 6 kilonewtons meters. So 12 kilonewtons meters, you can see 12 kilonewton meters, 24 kilonewton meters. So now what we do, we can just put this Q01. How do we put it? So you can look at that 4, 3, 5, and 2. You just do the sequence. And how do we put it? You can see this arrow going left to right. So we always put the near node first. So near node first, and near node verticals, and near node these rotations. And then this is far node verticals and rotation. That's the always sequence that we follow. Now, so therefore we have 4, 3, 5, and 2. What is the force in the 4? Going up, so positive 96 kilonewton. What is 3? 3 going this way, 96 kilonewton meters, 96 kilonewton meter going this way. 5 going up, so you have 96 kilonewtons, 96 kilonewton, and number 2 going this way, and that is opposite. Look at that. We have all right, so we have those two going this way. To going this way. So therefore we have opposite 96 going this way. Therefore we put negative signs. Now Q02, we have 24 and we have 12. So how does it work? Again, we can take these members. Number 2 and arrow. So you have near node is this, far node is this. What this is near node, this is far node, near node, far node, verticals and rotations, vertical and rotations. So we put 5, 2, 6, 1, 5, 2, 6 ones in that fashions. So 5, 2, 6, 1. So that would be 24, because you can remember that 5 is 24 and there is 12. Same directions. If it is in same direction, we put it positive. If it is in the opposite directions, we put it negative. So 24 going up and minus 12 kilonewton meters going on the opposite directions. So what we do, we assemble them, because you can look at that you have different different names are there. All right, so now here we will have 96, 5, 24. So at 5, you have 96 plus 24, 120. Number 1, minus 12, only 1. There is no any other number 1. So minus 12. Number 2, 12 and minus 96. 12 and minus 96, minus 84. Number 3, 96. Number 3, 96. Number 4, 96. Number 4, 96. And number 5, 120. Number 6, 24. Number 6, 24. So you can get all Q0 metrics with these 1 to 6 Q0 metrics that you can develop. So there are two metrics, Q metrics where you have a nodal displacements and Q0 metrics where you're gonna transfer it all into the nodals. Unmute yourself. Don't worry if you don't get the nitty-gritty things, but when I take the examples, I will take you through very slowly. Now in here, you don't need to remember this equation, by the way. When you have final exams, you are in the positions to carry one A4 page handwritten cheat sheet. Right? In your final exams, you can write whatever you like in your cheat sheet. So you don't need to remember anything. When you practice it, you can start preparing your cheat sheet right now. So you can have a one A4 page handwritten cheat sheet where you can put all the formulas, all the definitions, or whatever it's help you to do the examples. All right. Now let's move on to the examples that we want to complete. The examples are examples 1. We want to calculate the displacement here. What would be, let's say, A, B, and C. What would be the displacement? So if I draw the displacement curve, that would be your displacements. What would be your displacements, whatever the delta displacement that we have when you apply the load, and what would be the rotations as well that's applied here. So that's we need to calculate. Similarly here, what would be the rotation here? What would be rotation here? That's we need to calculate. We also need to calculate the reaction forces. What would be the reaction forces here using the stiffness methods? Last week we done pretty much both examples for stiffness methods. Now we are going further on that ones. So let me open that. All right. Week 4 and week 5. So I hope you remember these examples. Let me go through it with you. Let me go through it with you. All right, let me turn off my camera so you don't get these reflections. Okay, so here what is our plan? Our plan to do this modeling will be given to you. Okay, and based on these modelings, you remember that we plugged the values for the length and we found these stiffness metrics that you needed for K1. Then for element number 2, we calculate the K2 matrix as well. And then we combine K1 and K2 and we get the 6x6 matrix. Now, the next matrix that we want to get is this. Let me cancel this. That the relationship would be Q, which is the force, is equal to stiffness plus this Q0. Right? This is your force vector, nodal force vectors. What is nodal force vectors? Nodal force vectors meaning when the force are acting. Let's say you have beam here like this, and let's say the force is acting on the nodals. That is your nodal force. That is your nodal force. That's the what they're talking about. This is stiffness matrix. And that stiffness matrix we calculated this. You remember that from the last week. If you don't know that, you can calculate K1 and K2 by doing that one. And this is your displacement vector. And this is Q0, which is your member force vector. Right? Members force vectors where you have a force coming on to the members. Now let's develop. So far we got this. So far we get this K. We have not get anything else. We need to find the another values. So Q equal to how many degrees of freedoms we got? Look at that. How many total degree of freedoms? Come back here. We have total 1, 2, 3, 4, 5, 6. Total 6 degree of freedoms in the questions. So we can write 1, 2, 3, 4, 5, and 6. Let me get that figure here so we know what we're talking about. Copy and paste. So it's here, and we can get copy and can get paste. Now in here we have one. You can look at this one. There is no any force, so that is 0. Number 2, it's going up. You can see number 2 is going up, but 5 kilonewtons coming down. So we put -5 at 2. At 3, there is no any force, so 0. At 4, there is no any force, so that is 0. At 5, there is no any force, so that is 0. At 6, there is no any force, so that is 0. So I hope you understand how to develop the Q matrix. Let me know if you have any questions there. In developing the Q matrix, let me know if you have any questions. Q0 matrix is 0 because there is no any force on the members. You can see there is no any force on the members, right? There is no any force going on the members. All the forces are in the nodals, which is perfect. So all Q0 matrix would be 0, right? So now we can write the big matrix here with you. So what we're going to do it? We're gonna Q equal to KD plus Q0. Now we got Q. That's here. 0, -5, 3, 4, 5, and 6, 0. So there are 6 zeros. Oh, by the way, we need to find those reaction forces. So here 5 and 6 are not 0 because I can show it to you here. 5 has a roller support, you can see, and this will have a force here because that's roller supports. When the point cannot comes down, then it will create the reaction force. So that reaction force I can put it Q5. There is another reaction force which is the 6 because there is a pin support, so there is a Q6, right? So you can see this is Q6 and that is your Q5, right? Because these are your unknown forces. That's we need to find. So we can have Q5 and Q6, right? And equal to, we can copy this ones, K matrix, 2, -5, 1, 0, 1.5, 0, and so on. So we can just copy EI, 2, -1.5, 1, 0, 1.5, 0, -1.5, 1.5, -1.5, 0, -1.5, 0, 1, -1.5, 4, 1, 0, 1.5, 0, 0, 1, 2, -1.5, 1.5, 1.5, -1.5, 0, -1.5, 3, -1.5, 0, 0, 1.5, 1.5, -1.5, -1.5, and then D matrix. I think we did not develop D matrix. Let me develop D matrix, D vectors as well. So D vectors, let's say 1, 2, 3, 4, 5, and 6. Now, how do we do it? D matrix, you remember that free and fixed degree of freedom. So you can look at this one. So number 5 is fixed. Number 5 is fixed. Number 3 is free because that point can rotate. This 1 and 2 is free. 1 is free, 2 is free, and 4 is free, and 6 is fixed, right? Because this point cannot go, 6 cannot go down. So number 1 free. So free meaning it is unknown. So D1. Number 2 is free, which is your unknown. Number 3 is free, which is your unknown. D4, which is free, unknown. And D5 is your fix, and D6 is your fix, right? So that is your D matrix. I just copy them here. D1, D2, D3, D4, 0, 0. Right? And this Q0 is 0. There is no need to write it. So unmute yourself. I just substitute a value. There is nothing else I done. In the big matrix Q equal to KD plus Q0. I put this whole big matrix in up there. Okay. Questions then should be okay. We can continue. Okay, here. Now we do the partitions. When you see these 0 and Q5, so which is 1, 2, 3, and 4. Out 1, 2, 3, and 4. So 4, we do the partitions here. You can look at that, right? 1, 2, 3, 4, 5, and 6. I hope you understand how to draw this horizontal line because you can see Q5 and Q6. So that is basically your fixed and free degree of freedom. So if you look at here, when you started calculating your free degree of freedoms equal to 1, 2, 3, and 4. And your fixed degree of freedoms is your 5 and 6. Therefore, you have these fixed and free degree of freedoms. Now, for that case, we can also draw the vertical line. 1, 2, 3, 4. We draw vertical line here, right? So therefore, we can just put 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. I hope you understand how to draw these partitions. It's just drawing the line where the fixed degree of freedoms and free degree of freedoms, or you can see clearly here the partition zone. Horizontal line 4, vertical line 4. So now here I can just get these first vectors 0, minus 5, 0, 0 is equal to EI bracket. We can write 2 minus 1.5, 1, 0. 2 minus 1.5, 1, 0. Minus 1.5, 1.5. Minus 1.5, 0. 1 minus 1.5, 4, 1. 0, 0, 1, 2. So what I done? I copy these 4 by 4 matrix. I copy 1, 2, 3, 4. 1, 2, 3, 4. I copy these 4 by 4 matrix for you. And then you have this D1, D2, D3, and D4. Right? So those are your unknowns values and all. So if I write this matrix as a, let's say A equal to B, let's say this is X. This is unknown matrix X, right? So this is your A. This whole thing is your B, and this is your X. And I want to find this X. So what I do, I can do B inverse A equal to B inverse BX, and B inverse cancel out. So B inverse A equal to X. So if I can find the B inverse for these ones, I'm in the positions to be able to calculate the X. Now 4 by 4 matrix is difficult to do the inverse by hand. So what I'm planning to do it, I would like to do it this by Excel. Questions? The Q0 is 0 because when I take the next examples, it will be more clear. But let me explain you here as well that this is your original questions. You can see on my screen. This is your original questions. Where is your node? Your node are here. Node number 1, node number 2, and node number 3. This is your nodes. Node 1, 2, and 3. These are your different nodes. You look at the load, 5 kilonewtons. Where is it acting? There are only one load, which is 5 kilonewtons. One force, 5 kilonewtons, and that 5 kilonewtons load is acting at the node. at the node number 3. It's not acting slightly left of the node or exactly acting at the nodes. Therefore, Q0 is 0. If I have load here acting, let's say 2 kilonewtons, then I need to calculate the Q0. So I hope it makes sense that if you have a force acting not on the node, but on the members, then you need to calculate the Q0 that's using the tables. And I will show you that tables later. But does it answer your questions for this question that your force is only acting at the node, therefore your Q0 is 0. All right, so now so far so good. So now we have this 4x4 matrix, which we want to use the Excel. And we can just inverse it. So what we're going to do it, we're going to type 2 minus 1.5, 1, 0. So we're going to type 2 minus 1.5, 1, 0. Let me put it in the 4x4 format so we know what we're talking about. And in that format. And then you have minus 1.5, 1.5, minus 1.5, 0. Minus 1.5, 1.5, minus 1.5, and 0. Then 1, minus 1.5, 4, and 1. That is coming from here. 1 minus 1.5, 4, 1. 0, 0, 1, 2. 0, 0, 1, and 2. So if I want to do the M inverse, you can just highlight 4x4 matrix for me, like with the mouse. In your keyboard, equal to sign M inverse. You can type that, bracket, and you can just select whole range and enter. So you get this inverse matrix. So let me copy these ones. So that is your inverse matrix from the Excels. Let me put it here. Yep, here you go. We can copy that ones. So B inverse. So this will become 1 over EI. Let's say X is equal to B inverse A, 1 over EI. 2.67. Let's put 2 decimal places. 3.33. 0.67 minus 0.33. 3.33. 5.33. 1.33 minus 0.67. 0.67. 1.33. 0.67 minus 0.33. Minus 0.33 minus 0.67. 0.33, 0.67. Okay, so that is your B inverse, and the A matrix is this 0, minus 5, 0, minus 5, 0, 0. And this is your X matrix. Sorry, vectors D1, D2, D3, and D4. So if I want to get the D1 equal to 1 over EI, this whole thing 2.67 times 0 plus 3.33 times minus 5 plus 0.67 times 0 plus minus 0.33 times 0. So what I done? I just these ones and these ones, the horizontal columns and vertical columns. So if I just use my calculators, I would get minus 5, by the way. So minus 5 times 3.33, you get minus 16.65. So D1 equal to minus 16.65 on EI. And if we know the EI value, we can substitute that value. I think they have given the EI value, so let's put that EI value as well. I think in the examples, E equal to 200 gigapascals given here, 200 gigapascals, and I is 120 times 10 to the power 6. 120 times 10 to the power 6 millimeter to the power 4. Right, so we have load in kilonewtons. We have length in meters. That's the unit that we are working on. So for that, we need to get this one into the kilonewtons. 200 gigapascals meaning 10 to the power 9 pascals. So 201 pascals, you can write Newton per meter square. Now we need kilonewtons, so we can just over thousands to get it in kilonewton per meter square. So you get 200 times 10 raised to 6 kilonewton per meter square. So minus 16.65, 200 times 10 raised to 6 kilonewton per meter square. That is your E. I value, you have 120 times 10 raised to 6 millimeter power 4. So if I want to convert that one into the meter to the power 4, you just divide by 4 times. So 120 times 10 to the power 6 divided by thousands, divide by thousands, divide by thousands, divide by thousands. So you get 1.2 times 10 raised to 4 meter to the power 4. So 1.2 times 10 raised to 4 meter to the power 4. So minus divided by 200 times 10 to the power 6 times 1.2 times 10 to the power minus 4. You get 6.9 times 10 to the power 4 meter. And if you want in the millimeters, you can just times by thousands, or you can leave it in the millimeters. So you get 0.69 millimeters. What is that 0.69 minus? Because look at the D1. Where is D1? Here you go. Let me get that down here. Copy. Now, what is D1? That's what I want to explain. Copy. And paste. So you look at that. D1 is the rotation going in these directions. Now, minus sign indicate that you have rotations in these directions, and that rotation is minus 0.69, and I think it's in radian, not in millimeters. So that is radian. So that is minus 0.69. That's going in this opposite direction. Look at the direction here. Minus sign indicate that whatever you assume one, that is opposite to that that one. So that is the minus 69. D1. Similarly, we can calculate D2. D2 equal to 3.33 times 0 plus 5.33 times minus 5 plus 1.33 0 plus this one 0. So let me do it D2. D2 1 over EI. 1 over EI 3.33 times 0. 3.33 times 0 plus 5.33 times minus 5. 5.33 times minus 5 plus 1.33 times 0 plus minus 0.67 times 0 is equal to, so 5.33 times 5, you get minus 26.65 on EI. Similarly, you can substitute the value. E value was 200 times 10 to the power 6 kilonewton per meter square times by 1.2 times 10 raised to minus 4 meter to the power 4. So divided by 200 times 10 to the power 6 times by 1.2 times 10 to the power minus 4, you get 1.11 times 10 raised to minus 3 meter. And if you multiply by thousands, you get 1.11 millimeters. So here, these displacements that you can see, number 2 going minus, I think that is minus sign here, minus, minus, opposite. Because look at that, 2 is going up, but your displacements would be 1.11 going down. So that is just opposite to that value that you got it. So that is D2. Similarly, D3, you can get 0.670 this row by columns. So D3, 1 over EI, 0.67 times 0. 0.67 times 0 plus this third row, 1.33 times minus 5. 1.33 times minus 5. 0.67 times 0. And minus 0.33 times 0. So you get 1.33 times minus 5. You get minus 6.65 on EI. And we can substitute that value. 200 times 10 raised to 6 kilonewton per meter square times 1.2 times 10 raised to minus 4 meter to the power 4 is equal to 6.65 divided by 200 times 10 to the power 6 times by 1.2 times 10 to the power minus 4. You get 2.77 minus 10 raised to minus 4 meters. If you want in millimeters, then you just multiply by thousands, you get 0.277 millimeters. So what is 3? You can look at these figures. 3 is the rotations, and I think it's in radian. Radian, so that's 3 going in these directions. And if minus, meaning you have a these rotations going in these directions, which is 0.277. Last one, D4, 1 over EI minus 0.330 minus 0.330 plus minus 0.67 minus 0.67 times minus 5 minus 0.330 0.670 minus 0.330 and plus 0.670 is equal to 0.67 times 5. You get 3.35 on EI, which is positive. 3.35 on 200 times 10 raised to 6 kilonewton per meter square times by 1.2 times 10 raised to 4 meter to the power 4 divided by 200 times 10 to the power 6 times by 1.2 times 10 to the power minus 4. You got 1.40 times 10 raised to minus 4 meters. So would be 0.14 millimeters. You just multiply by 1000. All right, so that's all good. So that is your unknown value D1, D2, D3, and D4. So if I write it in that format, D1, D2, D3, and D4 is equal to 1 over EI. First one was minus 26.65. Second one was this is second one. The first one was minus 16.65. Minus 16.65 minus 26.65. And D3 minus 6.65. And D4 is 3.35. And if I substitute the EI value, I will get 0.14 here. And D3 was 0.277. And D2, I will get minus 111. Minus, this is minus by the way, 1.11. And D1, I will get minus 0.69. That is your final answers. Unmute yourself if you don't understand any of these values that I put it there. Examples with me. You remember this last week that we have these these examples here where we want to calculate this where we want to calculate this deflection and reaction. Oh, on that one, so I did not calculate the reaction force, by the way. Let me go back, please. There is one more questions that we need to find the reaction force. Now to find the reaction force, we can go back to this big matrix again and grab this Q5, Q6 from here. Oh, we disturbed these ones. That's okay. Q5 and Q6, we get it. And probably if you remember that whole these ones, it's written here 2 by 2, 1.5 and minus 1.5. So and 0, 0. So these, by the way, this is Q equal to KD. OK, and this Q0 is 0 is equal to EI 1.5 minus 1.5 0, 0. Where is coming from? Here, by the way. You remember this, we done it here. That is minus 1.5. Oh, sorry, 1.5 minus 1.5 0, 0. So that's value coming from here. And this 0 and minus 1.5 and 0, 0, 1.5 and 1.5. So 1.5. We need to get 4. 1.5 minus 1.5, 0, minus 1.5, 1.5, 1.5, and then you have D1, D2, D3, and D4. Right? So what I done, I grabbed this Q5, Q6, and all these 4 by 2 here, and I get this Q equal to KD. Now we can substitute the value D1, D2, D3. So Q5, Q6, EI 1.5 minus 1.5, 0, 1.5, 0, 0, 1.5, 1.5, and D1 and D2, D3, we can substitute this one, by the way, 1 over EI, minus 16.65, minus 26.65, minus 6.65, 3.35, and that's cancels. So this one cancels with this ones. So Q5 equal to 1.5 times by minus 16.65, we just row, plus minus 1.5, these numbers, times by minus 26.65, this is 0, times minus 6.65 plus minus 1.5 times 3.35. So if I solve this one, I would get 1.5 times by minus 16.65 plus minus 1.5 times by 26.65 plus minus 1.5 times by 3.35. You get 10 kilonewtons. Similarly, Q6 is your 0 times minus 16.65. This time I'm taking this one plus 0 times minus 26.65 plus 1.5 times minus 6.65 plus 1.5 times 3.35 is equal to 1.5 times by minus 6.65 plus 1.5 times by 3.35. You get 5 kilonewtons, which is minus. So what does Q5 and Q6 mean? You can come back here in the figure. Q5, you can going force here, which is 10 kilonewtons. Going up, positive meaning this direction 5 going up and going down is correct. And in here Q6 minus 5, nothing wrong with minus. It's just the sign is this side, which is 5 kilonewtons. You can see this 6 is going up, but when you get the minus, you just pointing it down. That's just opposite to what we got. All right, I hope you understand that. Let me know if you have before moving on to the next one. And in the last, we can do the space case. Okay, I think you remember these ones over here. We need to find the deflections in these particular problems. So we got K matrix. We got K matrix here. Now we need to find this relationship Q equal to KD plus Q0. Now first we get the Q matrix, which is the nodal matrix. Now for nodal matrix, let me get that figure back. Copy. Paste. And copy. And paste. All right, in here, you can look at that. You have number one. Number one is here, degree of freedom. There is no any load here. And that is number one is your free degree of freedoms. So number one is your free degree of freedoms. So at the free degree of freedoms, you have 0 force. There is no any force. And number one is free. Number two is also free degree of freedoms, and there is no any force here. So number two, how many we need to make it? We have total 6. So 1, 2, 3, 4, 5, and 6. Number two is 0 because there is just a free degree of freedom. Number two is also free degree of freedom. Now number three, which is your fixed degree of freedom. So Q3, Q4, fixed degree of freedoms. We need to find it, Q4. Q5, which is your fixed degree of freedoms, and Q6. So I hope you understand that this is your free degree of freedoms, and this is your fixed degree of freedom. Free, by the way, is just your values, and fixed meaning that you need to find it. Okay, so I hope you understand to develop the Q matrix. Unmute yourself if you don't understand to develop this Q matrix. All good? No questions? All right. Now we can develop this K matrix already there. Here, K matrix. D matrix we can develop. Oh, sorry. D matrix. Again, 1, 2, 3, 4, 5, and 6. Now in here, we have again 6 matrix. Sorry, 6 degree of freedoms. We just do it opposite to these ones because D1 and D2 is your free degree of freedoms that we need to find. And these are your fixed degree of freedoms, which are your unknown. So again, this is your free degree of freedoms. And this one is your fixed degree of freedoms, right? So I hope you understand how to develop Q matrix and how do you develop D matrix, and K we already calculated here. Now this is new Q0. Now how do we gonna go at the Q0? So let me grab this one down here. Okay. Okay, there you go. Now Q matrix, for that we need to use these tables. Table meaning here you go. These tables we need to use. Let me get these tables. These tables we need to use from the lecture notes. You can get these lecture notes, okay, on the LMS. And let's put that one here. Right. So these tables we need to use to get the Q0 matrix. Now for Q0 matrix, let's get the member number 1. Let's get the member number 1 for Q0. Member number 1. What is member 1 look like? Member 1 has 4 and 3. Member 1 has 4 and 3. So 4 is going up, 3 is going here. And 5 and 2. So this one 5 and 2 going this way. And it has a load of 32 kilonewton per meter. And the length, it has 6 meters. Length is a 6 meters. So now here, to calculate this Q0 matrix for member 1, we can have a, where is the arrow? Location vector is here. So location vector is here. Now in here, this is your near node. This is your far node. So first we write the near node, and near node is 4 going verticals, and the rotation is 3. Far node vertical is 2 and 5. I hope you understand this. 4, 3, 2, 5. Oh, sorry, 5, 2. Because vertical first and then rotations. So near node, this one near node, and this one far node, and this one is vertical and rotations. And rotations, verticals, and rotations. So I hope you understand that. Now Q0s. So we need to calculate this green color one. So you come back here, and in these figures you have W. So you can do WL on 2, WL on 2. So if I want to calculate this one here, WL on 2, W would be 32 kilonewton per meter. Length is 6 meters over 2. This is cancelled. So 96 kilonewtons. And similarly here, look at these figures, WL on 2. So 32 kilonewton per meter times 6 meters on 2, we get 96 kilometers. So 5 and 4 is done. So let me write it down. Number 4 going up, 96 kilonewtons. Number 5 going up, 96 kilonewtons. That's number 5. Number 3, moments. So here WL square on 2 going in this directions, WL square on 12. So if I substitute the value 32 kilonewton per meter, 6 meters square on 12, you get 96 kilonewton meters. I hope you understand what's going on. Unmute yourself or put it in the chat if you don't understand any of the details that I'm just putting it down here. And this one has a 96 kilonewton meters, and these values that you're gonna get is going which directions. You can look at this number number 2. Number 2 is going in this directions. So number 2 in this directions, but in the figure it is in this direction, so it will be minus. So that's calculation here, WL square on 2, which will be minus 96. I hope you understand why it is minus, right? Because look at in the figure, in the questions, the modeling, it shows this is the direction for 2. But when you do the calculations using these tables, which is this is clockwise, this is anti-clockwise, this is clockwise. So they are opposite, so therefore it is minus. Right, so I hope you understand for member number 1. For member number 2, same procedures. We can get this member number 2 here, B and C, 1 meter. So let me draw it up for you. This is member number 2, going 5 and 2. So there are 5 and 2. And here you got 6 and 1. 6 and 1. And this is near node. This is far node. So in here, you will get Q0 equal to near and far. 5, 2, 6, and 1. So we can do the calculation because the load is coming is how much? 48 kilonewtons. 48 kilonewtons, 1 meter here, 1 meter here. So if you look at this table again, P by 2, P by 2, both are going up. So here P by 2 equal to 48, which is given in our questions, divide by 2, 48 divided by 2. So number 5 is 24. Number 5 is 24 kilometers. Number 6, 24 kilometers. Number 2, PL on 8. Number 2, PL on 8. So 48 kilonewtons, 2 meters over 8. So that would be 6, so 12 kilonewton meters. So that would be 12 kilonewton meters positive, and that would be negative because look at this sign. This sign going in this clockwise, and look at this one is anti-clockwise. So therefore PL on 8 here, PL on 8, which is 48 times 2 on 8, which is giving me minus 12 kilonewton meters. So 5 to 6 ones. Right, so now we can get the big Q0 matrix by putting it 1, 2, 3, 4, 5, and 6. 1 is minus 12 here. There is no 1 here, so we put minus 12 kilonewton meters here. Number 2, positive 12 kilonewtons and minus 96. So minus 96 plus 12, you get minus 84. Number 3, 96, and there is no number 3, so 96 here. Number 4, 96, and there is no number 4 here, so 96. Number 5, 24, and 96. 96 plus 24, you get 120. And number 6, you have 24. Number 6, you have 24. So now we have everything. Q equal to KD plus Q0. We can substitute this value. Q equal to, let me get the details. Q equal to 0, 0, Q3, Q4, Q5, and Q6. I can show it to you. We got it right. Here you go. That is the Q. K matrix. We're gonna copy these whole things. Is equal to EI. And that would be 6 by 6 matrix. 2, 1, 0, 0, 1.5 minus 1.5. 1, 2.67, 0.33, 0.167, 1.33 minus 1.5. 0, 0.33. Probably if you draw a line here and line here, you don't need to write all these ones. You can just put dash because this one not be useful. You can look at the previous examples. These values, we're not going to use it. If you do it smartly, you don't need to copy that one. And you can just use this partition matrix that I show it to you here. Like this. And then D1, D matrix. I think we got D matrix here. D1, D2, and all 0. D1, D2, 2, 3, 4, all 0. And plus Q0 matrix. We got here minus 12, minus 12, minus 84, 96, 96, 120, and 24. So in here, you got 0, 0. I'm just copying this first part. EI 2, 1, 1, 2.67, and D1, D2 plus minus 12 minus 84. You can look at that. I just copied the whole first bit. If I bring this one across, that become positive 12, positive 84 equal to EI 2, 1, 1, 2.67, D1 and D2. Right. So again, let's say AB equal to X. And if I want to find this X, I can put B inverse A, B inverse B, X, and that's become 1. So I need to calculate this B inverse. I think 2 by 2 matrix by hand is possible. So, okay, let me show you this 2 by 2 matrix. So B equal to 2, 1, 1, 2.67. So if I want to get the dat B, then I need to multiply 2.67 minus 1, 1. So 2 times 2.67 minus 1, you get 4.34 as a dat B. What you need to do it? You need to swap this number by this number and you need to put minus here and you need to divide it by that 4.34. Now 2.67 on 4.34 minus 1 on 4.34 minus 1 on 4.34, 2 on 4.34. So 2.67 divided by 4.34, you get 0.62. You get 1 divided by 4.34. You get minus 0.23, minus 0.23. 2 divided by 4.34, you get 0.46. Right, so that's pretty much we can substitute a value that B inverse is 0.62 minus 0.23 minus 0.23, 0.46. That is your B inverse. What is your A matrix? 12 and 84. 12 and 84. And what is your X matrix? X matrix is D1 and D2. D1 and D2. So this horizontal line, verticals, 0.62 times 12 minus 0.23 times 84 equal to D1. Oh, that is 1 over EI, by the way, because remember there is a 1 over EI. This EI need to be inverse as well. See this whole thing divided by EI. 0.62 times 12 plus minus 0.23 times 84. You get D1 equal to minus 12 on EI, right? If I want to substitute the same value, like I think they did not give you the E value and I value in these examples. So if you want, we can just use the same one that we use in here, like 200 times 10 to the power 6. So 200 times, just for an examples, times by I value is I value here. I value here 1.2 times 10 to the minus 4 times 10 raised to minus 4 meter to the power 4. So 12 divided by 200 times 10 to the power 6 times 1.2 times 10 to the power minus 4. You get 5 times 10 raised to minus 4 meters. If you just multiply by thousands, you get 0.5 millimeters. So what is D1 represents? So here, if you come back here on this diagram here, D1 here, and if it is minus, meaning that it would be opposite, and you have 0.5 radian. That's your minus 5 represent. This is going this way. If it is positive, if your answer is negative, nothing wrong. You just change the sign. So that is your D1. Similarly, you can get a D2 equal to this minus 0.23, 0.46 minus 0.23 times 12 plus 0.46 times 84. So minus 0.23 times 12 plus 0.46 times 84, you get 36 on EI. Now, if you just want to put it in the full format, and you can just write in that one. So 36 divide, and it looks positive. 200 times 10 to the power 6 times by 1.2 times 10 raised to minus 4. 1.5 times 10 raised to minus 3 meters. So if you just multiply by thousands, you get 1.5 millimeters. So what is 2? You can look at the figure. And that 2 is the rotations, and that's positive because it's give you the same direction. So that is 2. Now we can calculate all these Q3, Q4, Q5, Q6. Let me write it down in that format. So Q3, Q4, Q5, Q6 is equal to EI 0, 0.333, 0, 0.167, 1.5, 1.333, minus 1.5, minus 1.5, D1, D2, plus 96, 96, 120, and 24. Like I just copy these ones from your big equations. I get this, get this, get this, and I get these 96, 96, 120, and 24. These guys here 4. Now we substitute this D1 and D2 here. Now D1 is minus 12 on EI and 36 on EI. So minus 12 and 36, 1 over EI. We can cancel this. So Q3 equal to this 0 times minus 12 plus this horizontal and vertical. 0.33336 plus 96. Right, you get 108. Q4 equal to this guys 0 times minus 12, 167 times 36 plus 96. You get 102. Q5 equal to 1.5 times minus 12 like this plus 1.33 times 36 plus 120. You get 150. Q6 you get minus 1.5 minus 12 plus minus 1.5 times 36 plus 24. You get minus 12. Now what is this Q3? 108 in the figure. Q3, here you go. 108 kilonewton meters. If it is positive, meaning same directions. Let me get these guys here. Copy. Paste. So Q3 meaning this 108 kilonewton meters. Q4 102. Q4 102 kilonewtons going up. Q5 150 kilonewtons going up, and Q6 minus 12 meaning it's gonna go down 12 kilonewtons. All right, so this is the whole story. I will show you this. We can do these examples first in the space case because it should give you the same results. These ones here. That's we can do it. So let me open the software space case. So I think you know how the space case works, right? Last week we done some work. So what we do it, we are working on this ones. We need to calculate this one. So you have pin support here, you have roller supports here, and you have 2 meters, 2 meters. So what we can do it in here, I think the units, you know that units are that's length meters, megapascals and all. Let me copy these ones for you so you know what unit we are using it, so you don't need to remember that. So let's get this one on the side. So these are the unit, don't change it, otherwise it will make your life. They will not gonna tell you. So just go to draw members, click on draw members here on the top, and then in your keyboard put 0 and hit enter. So it's automatically go to origin, and then you have first one is 2 meters. You can see these 2 meters here. So we can just put this way, and in your keyboard just put 2, and that is 2. Second one that you have 2 meters. So let me just put it horizontals, and in the keyboard 2 and escape key. If you want to remove this origin, just remove that origin and escape key to come out from the command. So we put this, we draw this one. Now in here, we can put these pin supports, and roller supports. So let me do that. If you double click on that one, there is a pin supports, which is your fix. The first three letters are fix, rotation fix, and there is a displacement fix, and the remaining three letters are for rotations fix, but there are two rotations allowed. Okay, Y and Z is allowed. So that's okay. We can put these ones here and hit OK. If you don't see these pin supports, you can just click on here. You will see these pin supports. Double click on here, and then if you go back to the figures, you have a roller support. So you have these roller supports. Again, first three letters are displacement about X, displacement about Y, displacement about Z, and then you have rotation about X, rotation about Y, and rotation about Z, and hit OK. So that's your pin supports and roller supports. Then you have a load 5 kilonewtons. So you can click on here, one click, and then nodal loads on the top here. If you click on nodal loads, don't put anything here. OK. And we need to have about Y axis, because look at this, X and Y. And we are opposite to the Y, we are going down. So therefore we put -5. We no need to put kilonewtons, kilonewtons written here. Hit OK and hit OK and hit OK. So you can see if going down, and that is your 5. And if you can't see 5, then you go here, so labeling and annotations, and so diagram annotations, and hit OK. You will see -5 kilonewtons there. Right, and we have these Young modulus and all. Remember these Young modulus and everything given to us. I can show it to you. Here you go, Young modulus and the moment of inertia given to you. What is the unit of Young modulus that we have? Megapascal. So we need in megapascals. So these would be your 10 to the power 9. I think the megapascals would be, if I want to have 200 kilonewtons, and megapascals meaning, here we can do it from here, that 200 times 10 raised to 6 times 10 raised to 3 Newton per millimeter square. Do you agree with me that I can write 10 to the power 9 as a 10 to the power 6 and 10 to the power 3? And this 10 to the power 6 is a mega, and this one is your pascals. So 200 times 10 to the power 3, 10 to the power 6 is mega, and Newton per millimeter square is pascal. So 200 thousands. So you agree with me that 200 thousands, this 30 is your megapascals. So that is your E. Let me go back. Sorry, just cancels. Double click on here, and the Young modulus here you put 1, 2, 1, 2, and 3, 200 thousands. And what we need, moment of inertia. We need moment of inertia here. The moment of inertia is in section properties is in millimeters. So that's OK. We have a section property in millimeters. There you go, 120 times 10 to the power 6. So 120 and 1, 2, 3, 4, 5, 6. Right, hit OK. Section 1 cannot be 0 cross sections area. OK, what generally I do it. Let me copy these ones. We just get some dummy sections. Let's say some dummy sections, and let's put 100 by 100, and then I will change it here. And then I will just change this one here, 1.2. So that's everything. These are not affected by any results. So then it will be happy. Hit OK. This one automatically picked up. You can see this is automatically picked up. Once you've done this analysis, linear static analysis, hit OK. Yep, it's completed. Now you want to see some results, right? Because we done the long calculations. We want to know what would be our reaction force, Q5 and Q6, right? That's Q5. Where is Q5? Here you go. Q5 is just trying to get okay. So here you go. So there you go, Q5 and Q6. So at here in the middles, you have 10 kilonewtons, right? So let's go and check. So if you want to check the reaction force, the button is here. So reactions, look at this, 10 kilonewtons, perfect, right? That's what we calculate. 10 kilonewtons here. And at 5 and 10 kilonewtons here. At 6, -5. At 6, -5. So opposite. So opposite -5 going down. So I hope it is makes sense. Now there is a displacements as well. You can turn off this and displacements. I think the displacements are not showing it up. So axial forces, no displacements. There you go, displacements. I think -16. Something wrong here. Probably -16. Did we get -16? Probably something that -16 D1. What would be your here D1 rotation? I think displacement is 2. So probably -1.11. Something is a little bit off, but that's okay. I think the procedures that you know, -16 or something else. Yep, -16. And that's the verification. I think they don't show the rotations, but I hope you got the drill. I hope you understand what we are trying to do. And I will show you one more that we done. This one we done. I can quickly show it to you. So 6 meters, 1 meter, 1 meters. So file, new, no. So draw members, 0 in your keyboard, and 6 meters, 1 meter, and 1 meters, and escape key, right? So 6 meters, 1 meters, and 1 meters. That's what we have, right? 6 meters, 1 meters, and 1 meters. Now for first 6 meters, you have 32 kilonewton per meters. So in here, we can use this instead of node loads, we can use these ones and hit OK. And in here, Y direction start positions, -32 and -32. And hit OK. Hit OK. You get, if you can't see that, you can go here. So diagram annotations. OK. So -32, -32. In here, you have another one, which is 48 kilonewtons. So in here, single click, nodal load, and Y -48. Hit OK and hit OK. So you have -48. Now you want to put a boundary condition as well. Sequence is not important, which one you go first, but you have fixed supports here, then roller supports here, roller supports here. So double click, fixed supports, that is the Ncaster fixed supports here. So fixed supports and hit OK. And then you have roller supports, roller supports. Roller supports and hit OK. And roller supports and hit OK. So then you can put these values are if you want to show these fixed supports, roller and roller here. Now we same thing. I think the material property was 200,000. You remember that 200,000, right? And then you have You can put the dummy cross sections like here, let's say 100 by 100, but we're gonna change this one to 120 and 1, 2, 3, 4, 5, 6, and then hit OK. And that's it. Analysis, linear static analysis. OK. Now you want to see the reaction forces. You can see 102, 150. Look at that. 102, 150 at Q4. So Q4 here, 102, 102. So Q4, 102. Look at this one here. Q5, 150. Q5 is 150. So Q5, 150. And 108 Q3. Where is the Q3? 108 Q3 moments. So 108 Q3 here. And the last one, Q6 minus 12. So Q6 is here, minus 12. Q6 minus 12 here, right? And I think displacements is not working properly, but we will check. Yeah, there is no any much displacement and rotations are not showing. But anyway, that's OK. Once is one verify, another one could be verify as well. So that's the overall procedures. Unmute yourself, ask questions. If I'm running fast or anything, you have more than welcome to just say which part you don't understand or anything. I will stick around here unless if you have any questions there. Any questions, anything about the subjects or anything that you want to?
Hi, sir.
Yes, please.
Regarding the assignment, sir, how do we
Yes.
need to submit the assignment after solving the problem on is it it has to be done on Excel sheet or it can be done on paper and we send you the picture of it?
So what you can do it, you can do the hand calculations on the
Yeah.
paper. You can do the hand calculation on the paper.
Yes.
Like
Okay.
which I show it to you. Which I show it to you. You know I was writing everything.
Yeah. In the video, yeah.
In the video. So
Yeah.
you do that once
Uh-huh.
in a piece of papers and you take a photo and make a one PDF file or something.
Uh-huh.
And for comparisons, I think you need to compare because when you compare, then you in the let's say you want to compare these results. So what you can do it, you can get let's say here, and you can get these figures with copy, and you can put it in the Word document and say this is my results. Let's say figure 1, reaction forces, right?
Uh-huh.
And then you can see the comparison. Your hand calculations, you need to compare. You can put your hand calculations here and so that this is matching.
Okay, sir.
OK.
Okay. Sir.
Does it make sense?
Yes, sir.
OK, let me find that ones for you as well. I'm just trying to find the examples.
The previous models.
I don't have any previous model because there's different changes, but I can show you one typical examples that can be useful for you. So let's say you want to have one examples here like this, right?
Yes, sir.
And let's say someone give you these ones and you calculate step number one, and then this is different methods, by the way. This
Yeah, yeah, yeah.
step number two, and then you
But I
you
got the
put,
idea.
yeah, you put it on the piece of paper like this
Uh-huh.
and scan it and
Uh-huh.
just put it there. But I also want to show you. So you just do the hand calculation, because the first questions you need to do the hand calculations,
Yes, sir.
and the second questions you need to compare that results. So let me find that as well. I'm just trying to find that one. Just give me a minute. I'm just trying to find that information. Just give me a minute, okay?
Okay, sir. Okay.
Okay, now I can share with you the screen. Now, when you do the, I think you don't need to comment everything. So you can include the space gas results, okay, in your
Okay.
software. Now, someone might say, how does it look like? So let's say someone give you this kind of a questions. You don't need to draw the shear force and bending moment diagram. So in here, you can just quickly write something, and I will send you these files as well by hand calculation. So you need to show that one, and a minor difference is noted between software and hand calculations. This difference is due to this 4.8. The calculator supports its beam does not carry any axial force. You just need to explain the theory and so on. And when you put these figures, you can see what is the roller supports, is the pin supports, and then you can just put the result saying this is reaction at support B, this is reaction at support B, and so on. You got my point?
Yes, sir.
Yeah, so you need to show your understanding. By the way, you don't need to follow exactly the same thing which I put it here, but you just
Yeah.
need to show your, we don't need this file, so don't worry about this page. This is for my other subjects, but yeah, I'm happy to send you these files on the LMS, so in the via email, so you will have it this one today.
In
Okay.
LMS, it will be available in week sessions, sir?
Just give me a minute. Where is available? I will show it to you. Uh, all right, I will show you where you can find it, and I will send you this one as well. Therefore, next week I've fully dedicated the whole 2 hours to help the students in their what can I say, in that all these kind of things that will stopping you to submit the assignments, or it's not clear.
Yes, sir.
Sometimes it's difficult when, so you want to see where you can find it. So this is your LMS page.
Yes, sir.
If you go on week number 5, space gas example can be found in this link. So you can click on here and you will be able to download that link,
Okay,
that
sir.
file, week
Okay.
number 5. Okay.
Okay, sir. Okay.
Okay. All right, any more? Can you draw a free body diagram for any one member with result force, or it is like as shown in the space case? Can you draw a free body diagram for any members with the result force, or is it like as shown in the space case? Now, there are two ways you can do it. You can draw the free body diagrams here. I can share the screen with you. So in the assignments, what you can do it at the final answers that you want to do it. So what you can do it in the final answers, you can just draw, let's say you can just draw, this is fixed, and let's say this is roller, and let's say this is roller. So in the free body diagrams, you can put 108 kilonewton meters, you put 102 kilonewtons. You can put 150 kilonewtons, and you can put 12 kilonewtons. So that is the one with your hand calculations. And then from the space case, what you can do it. Let's say you want to hide everything. Let's say you want to. I don't want loading, and I just want this snipping tools. Copy. So that is the free body diagram from the hand calculations, and this is the diagram from the space case. You can see the results 102, 102, 108.